In this video, we're going to be calculating, doing some stoichiometry with gases. This is exercise 15 in your packet. So exercise 15 says, a sample of methane gas having a volume of 2.8 liters at 25 degrees Celsius and 1.65 atm was mixed with a sample of oxygen gas having a volume of 35.0 liters at 31 degrees Celsius and 1.25 atm. The mixture was then ignited to form carbon dioxide and water. Calculate the volume of carbon dioxide formed at a pressure of 2.5 atm and a temperature of 125 degrees Celsius. So we need to figure out what is going on in this question. So we start with methane gas, and we know the volume of methane gas, and the temperature and the pressure. So if we have volume, temperature, and pressure, we can figure out the moles of methane gas. And it is mixed with a sample of oxygen gas. And we know the volume, temperature, and pressure of the oxygen gas. So then we can figure out the moles of the oxygen gas as well using the ideal gas law. So those are the two things that we start with. And then it's ignited, so this is a combustion reaction, and we form carbon dioxide and water. So those are our products. What we want to figure out in the end is our volume of carbon dioxide when we're given the pressure and temperature. So in order to figure out volume, if we're given pressure and temperature, we're going to need to find the moles of carbon dioxide. So just putting this in a mind map, we want to figure out the volume of carbon dioxide. So that's our end goal. In order to figure out the volume, we need the pressure, we need the temperature, and we need the moles. We already have the pressure, that's right here. We already have the temperature, that's right here. So we need to figure out the moles. Well, in order to figure out the moles, we're told that we're reacting methane gas with oxygen gas. So if we know the moles of methane gas and the moles of oxygen gas, then we can do simple stoichiometry using the reaction coefficients, the mole ratio, in order to figure out our moles. So we're going to get our moles from the reaction, and in the reaction, we need to figure out the moles of methane, and we need to figure out the moles of oxygen. And in order to do that, we need to know the pressure, the volume, and the temperature of both of those things, which we already have. So putting this in another way, we have a chemical reaction going on. We are told that methane and oxygen gas are reacting to form carbon dioxide and water. So let's balance this reaction so I'm balancing my hydrogens now. My carbons are already balanced, and now my oxygens, I have 2 more. Okay. So my ratio is 1 mole of methane for every 2 moles of oxygen. I'm going back here. I'm given 2.8 liters of methane, 25 degrees Celsius, 1.65 atm. So let's calculate our moles of methane. So hopefully when you plugged in all of those values in the PV equals nRT equation in the ideal gas law, you got 0.189 moles of methane. So now let's calculate our moles of oxygen. So we know that we have 35 liters, 31 degrees, and 1.25 atm. So we're doing the same thing. And hopefully when you plug in all those numbers, you get 1.75 moles of oxygen. So we have 0.189 moles of methane and 1.75 moles of oxygen. So what is our limiting reactant? What is going to dictate how much carbon dioxide forms? Well, we have a 2-to-1 ratio. So we need twice as much oxygen as we do methane. So do we have twice as much oxygen as we do methane? More than twice or less than twice? as much oxygen. Well, if we have 0.189 moles of methane, and we convert it into moles of oxygen, so that's 1 mole of methane for every 2 moles of oxygen, we would get about 0.38 moles of oxygen. Well, I want you to notice we have a lot more than 0.38 moles of oxygen. So that means our oxygen is in excess. So we're going to have leftover oxygen. Not all the oxygen is going to react, but all of our methane will react. So our methane is going to dictate how much carbon dioxide forms. I want you to notice we have a 1-to-1 ratio of carbon dioxide to methane. So if we have 0.189 moles of methane, we're going to have 0.189 moles of carbon dioxide. And this kind of shows how you do that stoichiometrically, but you can just really think about this. If we have 1 mole of methane for every 1 mole of carbon dioxide, we need the same amount of moles of both of those things. So we're also told the pressure of our carbon dioxide and the temperature of our carbon dioxide. We need to figure out the volume. So again, we're going to just use our ideal gas law, but this time we're going to rearrange it to solve for volume. So volume equals nRT over P, and we're going to plug in our numbers. We have 0.189 moles of carbon dioxide. We have 2.5 atm for the pressure, and 125 degrees Celsius. And again, whenever you're doing ideal gas law, make sure you convert your Celsius into Kelvin. So go ahead and pause the video, plug in all your numbers, and hopefully your answer matches mine. So I got 2.47 liters, and that is the volume of carbon dioxide. And when we look at this problem, I want you to notice the number of significant figures. So we have 3 significant figures here. This looks like 2, but when we convert it into Kelvin, we are adding 273, so we actually get 298 Kelvin, which is 3 significant figures. So this becomes 3 significant figures, 3 significant figures, 3 significant figures. Our temperature, again, we're adding 298, so that now has 3 significant figures. So I want you to notice everything has 3 significant figures, so our answer also has 3 significant figures.